Hi. So in this talk, I'm going to talk about pseudodeterminism with some promises and lower bounds. So my name is Pavan, and this is a joint work with Peter Dixon, Jason Vander, and NV Vinodchandran. So as the title suggests, this talk is about pseudodeterministic algorithms, and we present two sets of results, the promises that they hold. So informally, we're going to say that the designing pseudodeterministic algorithms will resolve quite a few long-standing open questions in the complexity theory. And our second part is about proving query complexity lower bounds against pseudodeterministic algorithms. Okay. So the outline of the talk is first we'll define the notion of pseudodeterministic algorithm, then talk about the promises that they offer, then we talk about the lower bounds and conclude with few open questions. So just to motivate the notion of pseudodeterministic algorithms, let's consider this problem. So given 1 to the n, the goal is to generate an n-bit prime number. So there is an obvious randomized algorithm for it that is efficient. We randomly pick an n-bit integer and check if it is a prime. If so, we output it. So even though this algorithm is very efficient, there's a drawback. So if I run this algorithm 2 different times, it's going to produce 2 different outputs with very high probability. So the different random choices will lead to different outputs. So in general, this is a feature of many probabilistic algorithms for search problems. Okay. So this motivates this question. Can we design a probabilistic algorithm that's going to consistently output the same prime? So along many random choices, I'm going to output the same prime. So motivated by this question, Gatt and Goldwasser formulated this notion of pseudodeterministic algorithm. So if we have a probabilistic algorithm A, we call it pseudodeterministic if on every input X, there is a canonical Y such that A outputs Y with probability at least 2/3. So it means most of the random choices of this probabilistic algorithm A will lead to canonical output Y. So pictorially to illustrate, so the algorithm here on the left is not pseudodeterministic because different random choices will give leads to different correct outputs like A, B, and D. So whereas on the right side, this is a pseudodeterministic algorithm. So almost all the random choices lead to the same canonical output A. Okay. So now in the work where they introduced the notion of pseudodeterministic algorithm, Gatt and Goldwasser proved or designed pseudodeterministic algorithm for few algebraic and number theoretic problems, such as finding non-roots of multivariate polynomials, finding non-residues, and finding generators of certain groups. And the works of Goldwasser, Grossman, Anari, and Vazrani designed pseudodeterministic NC algorithm for finding matchings in graphs. And when it comes to the prime generation, there's an interesting result by Oliveira and Santanam, who showed that there is a sub-exponential time pseudodeterministic algorithm for this problem, and this algorithm works at infinitely many lengths. So in addition, the notion of pseudodeterminism has been studied in several other contexts, such as sublinear algorithms, interactive proofs, streaming algorithms, and space-bounded computations. Okay, so let's talk about the acceptance probability of the circuit. So this seems to be a key problem in the study of pseudodeterminism. So this is a well-known problem. So given a Boolean circuit C, the goal is to estimate the acceptance probability of the circuit C. So if I randomly choose an input X, what's the probability that my circuit accepts this input? Okay. There is a simple probabilistic algorithm for this problem. You randomly choose 1 over epsilon square log 1 over delta inputs and evaluate C on each of these inputs and look at the fraction of the inputs on which C evaluates to 1 and output that fraction. And it's easy to see that this output is close to the actual acceptance probability with very high probability. But again, this algorithm is not pseudodeterministic. If I run this algorithm 2 different times, it's going to output 2 different approximate values with very high probability. So the question now we ask is that, can we design a pseudodeterministic algorithm for APEP, the acceptance probability estimation problem? Does it admit pseudodeterministic algorithms? Okay, so let's see what is known about this problem. So the work of Oliveira and Santanam and Woude, they showed that there is an average case sub-exponential time pseudodeterministic algorithm for APEP, and this works at infinitely many input lengths. And very recently, Lou, Olivera, and Santanam showed that if you can design a pseudodeterministic algorithm for APEP, then BP time admits hierarchy theorems. So if you look at the first result, that gives a hope that maybe there is a pseudodeterministic algorithm for APEP. And the second result shows that if we can indeed design such a pseudodeterministic algorithm, that's resolve a long-standing open question in complexity theory. We still do not know whether BP time admits hierarchy theorems or not. Okay. So another result known is due to Dixon, Pavan, and Vinodchandran, and who showed that APEP is complete in the context of pseudodeterminism. So which means if we can design a pseudodeterministic algorithm for APEP, then we can design a pseudodeterministic algorithm for quite a few other problems, many approximation algorithms and search BPP problems. So that's the currently known about this problem APEP, whether it admits pseudodeterministic algorithms or not. Okay. So now let's talk about the results, the promises part. So we're going to talk about the complexity theory consequences. So the informally going to say that the first result says that if we have a pseudodeterministic algorithm for APEP that explains the gap between promise classes and their language counterparts. And using this connection, we'll show that design of pseudodeterministic algorithm for APEP will resolve a few other interesting open questions from complexity theory. Okay. So let's look at the first results and talk about promise problems. The promise problems are introduced by Evans, Selman, and Yacobi in mid-80s. So a promise problem is nothing but a pair of disjoint sets called pi y and pi no. So often called as S instances and no instances. So we say that an algorithm that solves a promise problem pi, it should accept every input from pi y, and it should reject every input from pi no. And the algorithm may behave arbitrarily on inputs that do not belong to this pi y or pi no. And we say that a set S is a solution to the promise problem if it's a superset of all the S instances and it is disjoint from all the no instances. Okay. So now let's define this complexity class promise BPP. So given a promise problem pi, we say that it's in promise BPP if there is a probabilistic polynomial time algorithm that solves pi. So which means on every input from pi y, the algorithm accepts with probability at least 2/3, and on every input from pi no, the algorithm rejects with probability at least 2/3. And if you look at the inputs that are not in pi y or pi no, the algorithm may not have a BPP type behavior. That means on some inputs, it may accept with probability that's very close to half. Okay. So why are we interested in promise problems? Okay, so the question we're going to raise is that, is promise BPP equal to BPP? Does every problem in promise BPP has a solution in BPP? So why is this question interesting? So let's look at these questions. So if I can de-randomize BPP to P, does that imply de-randomization of MA to NP? Or if I look at the one-sided probabilistic class RP, if I can de-randomize to P, does that imply de-randomization of BPP to P? Or does BPP admit complete problems? For all these questions, we do not know the answers. But if you look at the promise analogs of these problems, we know an affirmative answers. So for example, we know that if promise BPP equal to P, then MA can be de-randomized to NP. And if promise RP equals to P, then that's sufficient to de-randomize BPP to P. And also it can be shown that promise BPP has complete problems. So this kind of suggests that the understanding the gap between promise problems and their language counterparts is very interesting. And that will shed light on these questions for which we do not know answers to it. Okay. So our first result relates the pseudodeterminism to this gap between promise BPP and BPP. So our result says that APEP admits pseudodeterministic algorithms if and only if promise BPP has a solution in BPP. So whether APEP has pseudodeterministic algorithms or not, it precisely characterizes the gap between promise problem and its language counterparts in the context of BPP. Okay. So let's give a proof sketch of this result. So if you look at the one direction, say APEP admits a pseudodeterministic algorithm. So A is a pseudodeterministic algorithm. So let's take a promise problem pi that is in promise BPP. So M is a probabilistic mission for pi. Now the goal is to design a solution to this promise problem that is in BPP. So you look at this algorithm P. On input X, look at the computation of M on X and convert into a circuit CX. So that is taking random bits as input. Now run our presumed pseudodeterministic algorithm A on this circuit C. If it outputs more than half, you accept, otherwise you reject. Now we're going to show that this algorithm B behaves in a BPP manner. Okay. So let's take an input X that is in pi y. Now we know that M accepts this X with probability at least 2/3. So the acceptance probability of this circuit is at least 2/3. So which means my pseudo-deterministic algorithm A, it's going to output a canonical value V that is more than half with very high probability. The most of the random choices will output this value V that is more than half. So B accepts with very high probability. Similarly, if an input is a no instance, B is going to reject with high probability. Now, what happens to the instances that are neither in pi y or pi no? Now, on these instances, let's fix one instance X. Let's say that M accepts the probability P. Now, the acceptance probability of the circuit is also P. And this could be close to half. But if I run my pseudo-deterministic algorithm A on this circuit, it's going to output canonical value V that is close to P, which means most of the parts of this A is going to output this fixed value V. And all these paths either will accept if V is more than half or will reject if V is less than half. So even on these inputs where the promise does not hold, my algorithm is going to either accept with probability more than 2/3 or reject with probability more than 2/3. So that means this B has a BPP type behavior. So the language accepted by B is a solution to this promise problem. Okay. On the other hand, suppose if promise BPP equal to BPP, now the goal is to design a pseudodeterministic algorithm for APEP. So for this, let's start with the standard probabilistic approximation algorithm for APEP. And we slightly modify it by rounding the output to closest multiple of epsilon. And it can be shown that we're going to get two possible outputs. Now we look at this promise problem. The S instances are all the circuit and the value pairs, where this algorithm M on the circuit C outputs this value with probability at least 3/8. And no instances are where my M outputs with probability at most 1/4. And it can be shown that this is in promise BPP. And if we have a solution to this promise problem, and using that solution, I can construct a pseudo-deterministic algorithm for APEP. So we'll skip the details of this proof. Okay, so using this equivalence between promise problems and pseudo-deterministic algorithms, we can obtain some consequences in complexity theory that relate to hierarchy theorem, circuit lower bounds, and complete problems. So first, let's look at the hierarchy theorem. So Barak showed that if promise BPP is same as BPP, then BPP admits a hierarchy theorem. So using this, we get an alternate proof of this result of Liu, Oliver, and Santana. If APEP has pseudo-deterministic algorithm, then promise BPP equal to BPP, and so BP time has hierarchy theorem. Now let's look at the second consequence, which is on circuit lower bounds. The question is that what's the smallest complexity class that does not have linear size circuits? We believe that P does not have linear size circuits, but we are far away from proving it. So what is known about this is Kanan showed that sigma 2 does not have linear size circuits, and that has been improved to the class ZPP to the NP. And currently the smallest complexity class that does not have linear size circuit is complexity class known as S2P. The question is that can we further improve this? Can we show that MA or NP does not have linear size circuits? So what can be shown is that if APEP has a pseudo-deterministic algorithm, then MA does not have linear size circuits. So how does the proof go through? So we start with this result of Santanam, who showed that promise MA does not have linear size circuits. And promise MA is nothing but there exists promise BPP. So if APEP has a pseudo-deterministic algorithm, promise BPP is same as BPP. So promise MA is there exists dot BPP, and which is a subset of MA. So we get that MA does not have linear size circuits. Okay. And using this equivalence, we get other consequences, such as if APEP has a pseudo-deterministic algorithm, we can construct complete problems for MA, and we can obtain hierarchy theorem for MA time also. Okay, so that's the first part of the talk, which talks about the promises. And now we're going to switch gears and talk about the lower bounds. And let's again look at the standard approximation algorithm for APEP, and we can convert that algorithm so that it's going to output at most 2 canonical values. So this algorithm, what we do is that you look at the interval 0, 1 and divide into subintervals of size epsilon, and you run the algorithm and round the output to the left end of the interval. Now it can be shown that we're going to have 2 distinct outputs. So motivated by this observation, Goldrake defined this notion of a k-pseudo-deterministic algorithm. So an algorithm, probabilistic algorithm, is k-pseudo-deterministic if for every input x, there is a canonical set Sx, which is of size at most k, and my A outputs a member of this X with probability at least k plus 1 over k plus 2. Okay, so now we look at this 2 APEP problem. So which is given two Boolean circuits C1 and C2. I want to simultaneously estimate the acceptance probabilities of both C1 and C2. And it's easy to design a 4 pseudodeterministic algorithm for this problem. So you run the 2 pseudodeterministic algorithm for C1 and then run the 2 pseudodeterministic algorithm for C2. And I get 4 possible outputs. Very interestingly, Goldreich showed that we can reduce the number of possibilities from 4 to 3. That means he showed that there is a 3 pseudodeterministic algorithm for this 2 APEP problem. Now, can you further reduce it? Can you go down from 3 to 2? Is there a 2 pseudodeterministic algorithm for this 2 circuit approximation problem? So our main result is that this is not possible using the known techniques. So the known algorithm to estimate the acceptance probability is uniformly generate an input and evaluate the circuit on that input. And using that uniform query model, we can show that there is no 2 pseudodeterministic algorithm for this 2 APEP problem. So this is the second main result in this work. So let me give a proof sketch of this. So let's assume that we have a 2 pseudodeterministic algorithm A for this 2 circuit approximation problem. Now look at this 2-dimensional square with side length n, which is like 2 to the n. Now we consider the standard grid partition of the square. And next, we look at an integer between 0 and n. I look at this circuit Cu, and this evaluates to 1 on the first u inputs, and it evaluates to 0 on the remaining inputs. We're going to argue the behavior of this algorithm A on inputs on circuits of this form. Now, coming back to this grid, for each lattice point UV, I'm associating a circuit pair Cu and Cv. Okay. So now I'm going to show this distance lemma. So let's take 2 lattice points P and Q that are adjacent. If I run my pseudodeterministic algorithm A on these circuits corresponding to P and the circuits corresponding to P, and if I look at output distributions, then we can show that the distance between these 2 output distributions is small. It's like polynomial over exponential. Okay, so that's the distance lemma that can be shown. And the next we're going to do is we look at a 3 coloring of this 0, 1 grid. Okay. So the first half is colored blue, and in the remaining half, we further subdivide and color half into yellow and other half into pink. Okay. Now look at the lattice point P from a n by n grid. And if I run my pseudodeterministic algorithm A on this one, there is a set of size 2, and it outputs a member of that set with probability at least 3/4. So which means it has a most likely output that's going to be output with probability at least 3/8. There is one output, this algorithm A is going to output with probability at least 3/8. Now, look at the most likely output. Let's call it AB. And this AB is going to lie in this grid. And so it's going to have one of these 3 colors. And color this lattice point UV with the color of AB. So here is a better figure illustrating this. If I look at this lattice point P, and if I run the algorithm A on the circuits corresponding to P, it's going to output, is going to lie in the pink region. So the lattice point P is colored, gets the color pink, and similarly lattice point Q gets the color Q. Okay. So now we can use Spooner lemma that shows that there is a unit square of this partition and whose corners have all these 3 colors. So which means if I look at this, my grid partition, there is a small unit grid and it has 4 corners. And if I look at the colors of these 4 corners, I have all these 3 colors appearing. So that can be shown using Spooner lemma. Okay. So now what does that mean? So let's fix a unit square with corners being different colors. And let's call them a P, Q, and R. So if I run my A on the circuit corresponding to P, the most likely output is A1, B1. And if I run my A on the circuits corresponding to Q, I get this A2, B2. And on R, I get this input A3, B3. Since P, Q, and R all got distinct colors, so that means that these tuples A1, B1, A2, B2, A3, B3, they're all distinct. And again, recall that the A1, B1, A2, B2, A3, B3 are the most likely outputs, and each of them are output with probability at least 3/8. Okay. So these are the 3 lattice points P, Q, and R. They are called all with different colors. And if I run my A on this circuit corresponding to P, which is like C, U1 and C1, and it's going to output A1 with B1 with probability at least 3/8. Now, if we apply distance lemma, so since Q is adjacent to P, if I run A on circuits corresponding to U1 and V1, it should output A2, B2 with probability close to 3/8. And similarly, the A must, on input this circuit corresponding to U1 and V1, it must also output this tuple A3, B3 also with probability close to 3/8. Again, that's because the lattice point R is close to P, and my distance lemma says that the output probabilities must be close. So which means my A must output all of these A1, B1 with probability at least 3/8, A2, B2 with probability close to 3/8, and A3, B3 with probability close to 3/8. But if I sum up all these probabilities, we get a value that's bigger than 1. So that's the contradiction. So this shows that A does not have a 2 pseudo-deterministic algorithm. Okay, so this result can be formulated in the context of query complexity. So just as a known result, the work of Goldreich, Goldwasser, Ron, and Goldwasser, Impagliazzo, Pitassi, and Santanam, they showed an exponential separation between the query complex of pseudo-deterministic algorithms and probabilistic algorithms. And using this earlier result, we get a finer separation. So this can be translated to show that there is exponential separation between the K plus 1 pseudo-deterministic query complexity and K pseudo-deterministic query complexity in this uniform and non-adaptive query models. Okay, so that's the end of this talk. Just would like to mention a few open problems. So an interesting question is that if I have a pseudo-deterministic algorithm for APEP, now we can show that MA does not have linear size circuits. Can we improve it to show that NP does not have linear size circuits? Or can we show that such a pseudo-deterministic algorithm will de-randomize MA to NP? And similarly, does a pseudo-deterministic algorithm for APEP, does it imply BPP is same as RP? And another interesting open problem is to find a pseudo-deterministic algorithm for the prime generation problem, or if not a pseudo-deterministic algorithm, can it find a poly pseudo-deterministic algorithm for the prime generation problem? And can we improve our lower bounds to the general query model? Okay. So finally, we would like to dedicate this work to Alan Selman, who has done seminal work on promise problems. And Alan also studied the notion of pseudo-determinism in the context of non-deterministic computations. Thank you very much.